Hi folks, this is Shefik. In this video, we are going to talk about my recent open source project about lightweight elliptic curve cryptography for Python. But before we begin, please like the video and do not forget to subscribe to the channel to stay up to date with the latest videos. Also, your comments are more than welcome. Thank you for your all support in advance. First thing first, there are many forms of elliptic curves. Weierstrass, Koblitz, and Edwards are popular forms of elliptic curves. Each elliptic curve form requires different methods for its arithmetic. For instance, Weierstrass form and also Koblitz form involve drawing a line that passes through 2 points as illustrated here, and the intersections reflection across the x-axis represents the addition of those 2 points. Doubling a point also involves drawing a tangent line as illustrated here in Weierstrass and Koblitz forms. On the other hand, Edwards curves rely on formulas that cannot be visualized with lines. We have addition formulas as illustrated here in Edwards curves. Moreover, Weierstrass and Koblitz forms have distinct formulas for addition. For instance, this is addition formula, and doubling. This is the doubling formula for Weierstrass form. On the other hand, Edwards forms have same formula for point addition and point doubling. Furthermore, the Weierstrass form is symmetric about the x-axis and making it easy to find the negative point of a given point by reflecting it across the x-axis. On the other hand, Koblitz form is not symmetric as illustrated here, and it requires a different formula to negate a point. And finally, Edwards form requires considering the natural element in order to find the negative point of a given point. I know I explained so many concepts, but the question is, do you have to know them all if you're a practitioner? The answer is no with light ECC library, and in this video I'm going to show you a demo with light elliptic curve cryptography library with a few lines of code. If you haven't installed light ECC library before, you need to run pip install light ECC command, and this is going to install the Python package into your environment. Thereafter, you will be able to import the library as from light ECC import light ECC. In this experiment, I'm using its 0.02 version. Thereafter, I'm going to construct an elliptic curve as elliptic curve is going to be. Here I'm going to initialize light ECC object. If I run this command, this is going to construct an elliptic curve in Weierstrass form because its default value is Weierstrass. On the other hand, I can set its form to any other form. Form name is going to be, for instance, Edwards. As mentioned, alternatively, I can set this to Weierstrass or Koblitz too. And secondly, I'm able to set the curve name. Here I'm going to set the curve name as @25519. Here you can find the supported curves in the supported curves section in the readme of the repository. For instance, in Edwards form, @25519 is the default one. You can switch to any other one here, or these are the supported curves for Weierstrass form. And finally, these are the supported curves for the Koblitz form. In this experiment, I'm going to use this @25519. But if you haven't set anything to form name, then it's going to use Weierstrass form and SecP 256K1. This is the default one, and this is used in the Bitcoin. My elliptic curve is constructed, and I'm going to get the base point of this curve. If I get the constructed curves.g, this is going to give the base point. Actually, this is a point on this elliptic curve, and this is a publicly known value. This is going to be used as a generator point. That's why we are using g. As you can see, it has x and y coordinates. Now let's talk about point additions over elliptic curves. With light ECC, I can use regular mathematical operators to point additions or any other calculations. For instance, if I add g to itself, I'm going to get 2g, and this is the coordinate for the 2g. Let's say 2g. Similarly, if I want to find the 3g, I can add 2g to g, and this is going to be, this is the coordinates of point 3g. Now let's add 3g to 2g. This is going to be 5g. Let's print its coordinates again. Similarly, I'm able to perform subtraction operation here. For instance, 5g minus g, this is going to be 4g. I should get the same value by adding 3g to g. As you can see, they are returning same. Point addition in elliptic curves require to perform a basic formula, and its complexity is constant time. In other words, it requires O1 complexity. Let's say O1. Now let's talk about multiplications. Suppose that I want to find 50g. What should I do? I need to multiply 52 base point g. This is going to give the coordinates of 50g. Or we can change this to a larger number, 2500. This is the coordinate of 2500g. Here in the background we are using double and add method, and its complexity is O log n. In other words, even if you want to find a very big number, you can find it very fast. Finally, let's talk about the division. I have the coordinates of 2500g, but suppose that I have just coordinates. I don't know which point is this. If I divide this to base point g, I'm going to find the multiplier, that's 2500, what division operator, but this requires to perform root and first method, and its complexity is O(n), which is very high because in real world we are using very large numbers here instead of 2500. This makes elliptic curve cryptography very powerful. Actually, this is called elliptic curve discrete logarithm problem, or shortly ECDLP. This makes elliptic curves very powerful because when you have a coordinate, we know that this on the elliptic curve, and this is retrieved by multiplying the base point g to some constant k, and finding k is really hard. On the other hand, if you have the value k, I mean for example 2500 here, if you know that value, also you know the base point, it's very fast to find the multiplication. So in this video we used light ECC library to perform elliptic curve cryptography arithmetic operations in Python with a few lines of code, and we don't have to know the process behind elliptic curves. We are able to adopt any kind of form, including Weierstrass, Koblitz, and Edwards. Also, we are able to adopt any curve for those given forms, and we are able to do it with regular mathematical operations. So, if you do like this video, please like it, and do not forget to subscribe to the video. Also, if you make comments in this video, it will help me to reach much more people. I'd be appreciated in that case. Thank you all for watching, and see you next time.